I didn't even know that was an option.
Oh, yeah, no, I love it. Until you try to
I
find
spent
it.
half an hour deleting stuff from my computer, and it turns out you can just save it to the cloud.
All right, okay, we'll get started. So this is a very well-attended PhD dissertation defense. I'm really, okay, fine, okay. So first of all, welcome on this, like, what is it? Tuesday in August. It's really exciting to have you all here today for, Galahad Wernsing's very special day. My name is Alex Wodlinski, so I am a professor of electrical and computer engineering. I'm also the Associate Dean of Graduate Studies here at WPI. We're here today for the third of three critical requirements of any PhD student in WPI's Electrical and Computer Engineering Department, which is the PhD dissertation defense. The purpose of this dissertation defense is for the PhD student to present sort of the culmination of their works throughout their PhD studies here at WPI to, first of all, an open audience, right? So the committee members are here, who I'll introduce in a few minutes, as well as the chair of the dissertation committee. So that's going to take approximately 45 minutes of presentation slides, right? And then after that, the PhD student will answer questions from the general audience about what they've done. Like, it could be like very many details to very sort of like big picture, why is this, where can you go with this, and all that jazz, right? After which we'll ask the general audience to leave, and only the committee will stay, because unlike the rest of you, we had an awesome book to read, each and every one of us, leading up to this. And so the presentation really kind of summarizes many of the key aspects of what that PhD dissertation document is. So very importantly, even though this is not archival, the dissertation is and will be shared openly in the WPI library through digital.wpi.edu. So a little bit about Galahad. So Galahad and I crossed paths many years ago. I think it started with MQP.
No, I took 2305.
You took 2305. You took 2305, and then you and Jimmy and Gage did your MQP with me on building a custom built electric car harness for basically the Team SAE custom race cars as part of their MQP. I believe it won the departmental provost competition that year. So yay! And then Galahad said, "This Wodlinski guy is cool, so I'm going to stick around for a couple of years and do a master's thesis with him." And yeah, you did one, and then that's when you got exposed. You're going to see the acronym BLE said an awful lot in this dissertation. Bluetooth Low Energy. That is essentially the standard that we all use when we have a Bluetooth device. And since then, just like in The Godfather, I tried to get out, but they keep pulling me back in. BLE has always been sort of surrounding Galahad's existence. So following the master's thesis, I said, Galahad, you want to do a PhD? And Galahad, I forgot which color pill, but essentially said, I'm going to do the PhD with you, Wodlinski. And so we jumped into this journey together. And that's really important, because a PhD is a journey of it's a partnership between advisor and advisee. And together, unlike your typical electrical and computer engineering PhD dissertation, Galahad went the route of how can we transform wireless communications engineering to the 21st century? Let's stop teaching it in a way that I learned it in the 1990s, somebody learned it in the 1980s, how it's even being taught now. We got these really cool tools, which you're going to be hearing about. And it's like, now that combined with project-based learning, combined with open source software packages and how can we rethink how this is done? And through 3 years of teaching assistantships, Galahad put that to the test. And you're going to see a lot of the culmination of that journey transform into what is now the dissertation. So you might say, well, isn't that an engineering education dissertation? Shouldn't that be in a different department? No, because it's still rooted very much in technology. And sure, there are different aspects. Hello, come on in. Even though the journey itself is sounds like we're changing pedagogy, it's still rooted very much in technology. Come on in. That is only really core to any person with PhD level competency in electrical engineering. So before I continue and let Galahad take the floor, I really want to sincerely thank both members of the committee. So Bill Michelson, he's a professor of enough, like, I don't even know which department anymore, but Bill is essentially, has been here quite a while at WPI, extremely knowledgeable, and has appointments across, I think, 5 or 6 departments: ECE, robotics, mechanical, computer engineering, computer science. Any others I missed so far?
I guess I'm part of this new AI master's program.
The AI master's program. But the idea is the perspective on design and engineering and science and applied to education is really important. Right? And then there needs to be an external committee member, and we have very thankfully Professor Robert Walls from computer science. And very importantly, Professor Wall's perspective is also very much applied as technology meets society, and there's been a lot of interactions between both Professor Walls and Galahad. So I just want to thank you both for serving this very, very important role, especially as it's culminating this day. So with that, I'm going to turn the floor over to Galahad, and let's first wish him well in terms of getting this presentation going.
All right, so my slides are up on the TV. Can anyone on Zoom tell me if the audio is good in the chat?
So great, Galahad.
Great, thank you. As Professor Woodwinski said, I'm Galahad Wernsing. I've been working for these last 5 years on undergraduate software-defined radio education. I would have spelled out the acronym, but it didn't fit. We're joined by my other committee members, Dr. Michelson and Dr. Walls. And it'd be really cool. My slides advanced. Yeah. All right. I had to skip every single part of electrical engineering background information you'd need just to get everything else in. So if you don't know what I'm saying, just either type it into the chat or raise your hand and go, hey, I don't know what whatever is. Outline. I'm going to give you the background that I didn't skip, talk about the lab series that I created and then ran for 3 years, along with changes to the lab series between years. Then we're going to discuss course evaluation data from the students that we got. And then we will move into some other work that I did that doesn't directly relate to the students I taught, including a code framework for future students to use, trying to get ChatGPT to solve the problem, and if someone else picks up the torch, where would you go from here? And then we'll have the Q&A. So the original problem statement, or the overarching problem statement for what I did, was how do you effectively teach an upperclassman how to use a software-defined radio in a 7-week course? And for those of you that aren't from the WPI community, we do everything in quarters. So the timeline is very compressed compared to a semester, which means you have to be very efficient in how you structure your labs to make sure that you can get all of the information conveyed without too much student stumbling, because anything you do that takes extra time pushes information off the end of the course and you won't be able to get to it. The project goals are to take the total amount of information you need to learn to use one of these at a basic level and sort of bring that level down so that it's easier to stuff all that information into the lab series. We'd like to reduce the learning curve from getting from the position of a novice, like, I don't know what this thing is that I'm holding, to I can now use it. The sort of traditional approach involves some pretty big jumps in required understanding. I'd like to give students tools to work further on their own, because there's only so far I can take you in 7 weeks, and I hope to, instill the desire to keep going, give them the ability to keep going, and encourage students to sort of poke around and learn stuff on their own. Again, that's in part driven by just in interest in teaching and partially driven by the constraints of the 7-week schedule that we're operating within. What is a software-defined radio? Traditional radio does all of its data processing in hardware, and it's not particularly flexible. So the radio in your car can do AM, FM, Bluetooth, but it can't connect to your home Wi-Fi network because it doesn't have the radio hardware to do that. And your phone can do, say, Bluetooth and Wi-Fi, so it has the Bluetooth in common with your car radio, but it can't do AM and FM. There's this other class of device called a software-defined radio, where the hardware is quite capable, but you, the little monkey at the computer, have to program all of the information processing that it does. So you just get a description of the radio information coming in, but the hardware doesn't know how to turn that into something usable to a human. So you have to program all of that. And this is the general block diagram for the receiver side of a software-defined radio. We'll be focusing on the receiver side because the transmitter side, you just reverse all the arrows. So it's largely the same things, but backwards. And the class also has a focus on receiving data because you can get in a lot of trouble if you transmit without licenses. And we don't want our students to get knocks on their door from the government. And one key piece of information for later is right in the middle between the ADC and the DDC. You get complex values if you're a math person. So you've got imaginary numbers you're working with, which isn't really a problem for a computer, but it'll come up in some steps later. We're working with Bluetooth Low Energy. What is it? It was originally designed so that there's two versions of Bluetooth. There's Bluetooth Classic, it's called now, and Bluetooth Low Energy. Bluetooth Classic was this attempt from the very early 2000s to try and replace hardware serial cables with some sort of wireless link. It sucks. They decided to scrap the whole thing essentially and replace it with Bluetooth Low Energy. They took the good ideas, converted it to a lower power format, and essentially the only things it's used for from a consumer perspective are wireless audio and connecting to your smartwatch. But everyone has a smartphone, and every smartphone has Bluetooth Low Energy. So all of my students are going to have access to something that transmits this type of radio waveform. And yeah, cool. The other important part of that is that there's a subset of packets that are unencrypted, which means you as a third-party observer to the communication link can still understand information being transmitted between the two devices that are talking to each other. All of my work was done in ECE 4305, Software-Defined Radios, Systems and Analysis. It is offered once a year, third quarter, so right after winter break. It is a 7-week course, and there are 2 suggested courses that come in front of it purely in the communications division. There's something on the order of 6 classes that are, if you follow the completely recommended schedule, you would end up taking before you hit it. But there's a 2000 level communications course, and there's a 3000 level communications course. Something like half the students skip the 3000 level. I did too. It does make taking 4305 a little bit harder because you need to learn all the information from the 3000 level yourself, but it does make scheduling easier because you have to take fewer classes in a specific order, and some things are only offered once a year, so it can be hard to line all of these up. So why should we do this project? Coming into the project, there were some known flaws in the approach in the existing 4305 lab series, both from when I took it in 2018 and subsequent years. And looking outside of WPI, existing approaches to teaching have not been examined recently, if ever, like examined as a topic itself. And in the past 5 or 10 years, the hardware and software landscape for software-defined radios has come a huge way, especially for sort of the beginning stages of using one of these. So at the higher level of performance, where you already know what you're doing, the capabilities have largely been set up for a long time, but bringing the access to that lower in skill level has come a long way recently. Looking at other schools, I spent a few days to 2 weeks just Googling every combination of software-defined radio course college. And I found 25 total US-based academic institutions that offer some kind of course in software-defined radios. 13 of them were offered at the undergraduate level, 12 at the graduate, and a smattering of others at either the continuing education level for existing professionals, and one school actually had a camp for high school students that was offered last summer, but they don't have a formal course. So that was interesting. Most of these are not offered anymore. I could only confirm that 10 of the courses are currently offered. And I could confirm that 8 of the other 15 are no longer offered. And very few schools offer both undergraduate and graduate levels. So if you're at a given institution, it's sort of a crapshoot. Even if you have a course in this at all, if you're interested, and if it's at an appropriate level for where you are in your education. Looking at this from like a journal publishing perspective, there aren't very many publications in this area at all. And most existing publications are examining taking approaches and project concepts that you would use in a research lab for graduate students and adapting them into a course, instead of saying, how do I design a course from scratch with the knowledge that this is how I will end up using them in research. And I only found 2 or 3 that were looking at specifically moving to newer hardware and moving to newer software suites that are currently available. For the hardware choice specifically, we went in looking for something that a student could purchase for the cost of a textbook, because we've got a free textbook that we're using written by Dr. Waglinski sitting here in the corner. So we were looking for a radio that a student could buy for roughly the cost of a new textbook. But most of the schools that I found information for used very expensive research radios. We're talking entry into the product line is $1,300. We have some of these pushing 5 figures upstairs in the lab. So these aren't things that students can really explore with. You can't run around with it connected to your laptop looking at, what's a microwave oven look like? Can I find different radio stations in different parts of town? Because these are pretty delicate. You don't want to do anything that might damage them, and they can't leave the building. And there aren't all that many options in the price range we were looking at. So this is a shortened list of what I found. And this is what's available for less than about $300, which was sort of the upper cost that we were looking at. And some of the background information that I skipped is a lot of the signals that you will want to look at as sort of an introductory user are right around 2.4 gigahertz. So we would prefer to have a radio that could support the 2.4 gigahertz region. With that requirement, we're down to 3 radios here. We're looking at the Pluto Plus, the Pluto, and the Caribou Light. When we were deciding what radio to use in, man, when did you switch radios? The 2019 course?
Yeah. Yeah, no.
No, it was the 2018 course because I have.
Yeah.
Yeah, we switched to those in 2018. So we were already using this radio by the time I entered the this project. We ended up using the Plutos in part because they're a good balance between cost and usability. Yeah.
Just FYI, like when they first came out, they were $150.
Yeah.
And because of inflation,
Yeah, so, and when they first came out, the Pluto Plus didn't exist because that is the Pluto is technically an open source project and you pay the manufacturer to build it for you and, you know, put it in a box. The Pluto Plus is an upgrade to that, but you buy them on AliExpress and we don't really want to have our students ordering things speed pack from China. And the Caribou Light only came out a year ago. So at the time, there was only really one option that covered the 2.4 region. And it, yes.
So what is 2.4 of a particular interest?
2.4 is a particular interest because it is in a category of frequency regions called ISM bands for industrial, scientific, and medical, where the FCC, the government agency in charge of frequency allocations in the US, decided that there's these certain regions that you can use for whatever you want. You don't need special licenses or anything. So Wi-Fi and Bluetooth are up at 2.4, along with some other more obscure communications protocols. And if we're already operating in that region and a student decides to screw around and transmit something that isn't illegal, the other region of interest would be the 900 megahertz band, which almost everything on the chart supports. And that's for longer range, lower data rate things. Like if you want to have a little walkie-talkie that broadcasts a kilometer, you do it in the 900 region. And we're looking at Bluetooth Low Energy, which exists in the 2.4 band. Software choices. A lot of schools don't say what software they're using. I don't really know why. It would be cool if in the course description they said, oh yeah, we're using GNU radio and this model radio, and we're looking at these signals, and none of them do. Most schools use either GNU Radio or LabVIEW, which are both visual programming languages where you drag and drop blocks and move little arrows between them to link them up. Then a couple of schools use MATLAB and Simulink, which is MATLAB but different. And we are the only school that I found to explicitly use Python as the only language in the software-defined radio course. We were looking to strike a balance between usability for the student and usability for future efforts the student might have. So looking at LabVIEW or MATLAB, those have a really high ceiling for what you can end up doing. But the entry cost is very high because very few students know how to use MATLAB coming into the course. Nobody's going to know how to use LabVIEW, and they're rather difficult to pick up as programming languages. So when I took the course, we were using the Plutos, but we were doing it in MATLAB, and I had a little bit of MATLAB experience, but it was still difficult to get the hardware to do what I wanted, even when I knew what I wanted to do, because I was struggling using MATLAB, where students generally find Python easier to use. And at WPI specifically, the non-majors introductory computer science course is taught in Python. So a lot of our students come in with an amount of Python background and spend less time fighting with the programming language, given our choice here. And why are we using Bluetooth Low Energy? I came into the project right at the beginning of our favorite pandemic lockdown. And we needed all the courses were remote, and we needed something that students could look at in Nebraska and here and wherever they were, because we couldn't say, oh, I have this little transmitter on my desk, take a look at what I'm doing, which is the experience I had. And it's within the supported frequency range of the Pluto. It does have unencrypted messages, which is important for students to be able to actually process the data. And I already knew how it worked because my master's degree was working on Bluetooth Low Energy. So it was pretty easy to go from that straight into, okay, now I'm using this and I'm teaching a student how to use it, instead of I have to learn this and also teach a student how to use it at the same time. Getting into the specifics of what I did, I designed a complete lab series for a 7-week course that the first version worked remotely. It works towards a single goal. And in large part because of that, it went more smoothly than the lab series offered in previous years, which suffered from variously ill-defined goals, issues with the specific broadcast standard we were using, or goals that were dynamic during the course. Getting into what the labs specifically are. There's 5 labs I will go over. The first 2 are designed to get you to make and understand this plot. This is called a spectrogram. So the radio frequency region has, you can go from lower frequency 900 megahertz all the way up to 2.4 gigahertz. A lot of the research radios that people use tend to support up to about 6 gigahertz. And this is looking at, on the x-axis, this is a small section of the radio frequency region centered around 2.4 gigahertz. This is about 50 megahertz wide. And then the y-axis is time increasing up. And we can see 3 pretty important things from this plot. The first is the little rectangles are Bluetooth Low Energy broadcasts. So one device is broadcasting to another one in some sort of negotiated Bluetooth link, and you're seeing the packets that are being broadcast there. The second is this larger, dimmer rectangle, sort of in the middle, slightly to the left, is a Wi-Fi packet. So you can see the difference between the two. You can also get a handle, sort of a vague sense for why you can stuff more data through Wi-Fi than Bluetooth, and it has to do with the width of what you're broadcasting. And the third really important thing from this plot that students should be able to recognize is that on the right-hand side, the dimmer green rectangles are a mirrored reflection of the red ones on the left, which is an artifact of data processing. There aren't actually packets there. So it'd be, at the end of these labs, it would be good if students could look at this and say, oh yeah, that's a Wi-Fi packet, those are Bluetooth packets, and those are some processing artifacts. And I've gotten my hardware to the point where I can run some code on my computer and generate this plot. The third lab is looking at Bluetooth specifically. So Bluetooth Low Energy is split up into a bunch of narrow channels that you can broadcast on. And you can sort of see that these red blocks are in 3 sort of vertical bands, right? And each one of those would be a channel. Inside of the channel, the Bluetooth packet isn't necessarily centered because the broadcaster and the receiver don't know exactly what frequency the other thinks they're operating on. Because if they did, you could just send the data you're sending over whatever communication system they had to negotiate that. The Lab 3 is designed to take the data, which is offset, and therefore you can't directly turn the data into whatever bit stream the computer is expecting and recenter that. And the way you do that is if you take this plot on the left showing sort of the center line of what's being broadcast and the two side peaks and look at it. So if you were sort of driving along this in a car and look at it out the windshield, you'd see some peaks where the 2 side broadcasts are in the center one. And if you could do a mathematical calculation to find where the center of mass of this plot is, and because the background noise is so much lower than the broadcast power of your Bluetooth packet, the center of mass of the broadcast is very close to the actual center of the broadcast that the transmitter is sending. So you can, if you calculate the center of mass, you can then calculate an adjustment to take your entire plot and shift it so that your data is nicely centered and well balanced between the 2 sides. Lab 4 is the hard one that everyone complained about. Because what you have to do is fix dynamic frequency alignment problems. So if we go back to the driving on a road analogy, if you're trying to follow the person in front of you and pay attention to what they're doing, they're going to be wandering back and forth in the lane a little bit. And to properly decode the signal, you need to be straight behind them. So you need to program in somehow a way to correct out that wandering. To get into actual data plots, here is, and this is where we get back to, I mentioned earlier that we're working with complex numbers. This is a plot of just the real magnitude of a Bluetooth packet. So we stripped out the imaginary part just for plotting. And you can see, you know, right at the beginning, the magnitude's very small. That's just the background noise. The magnitude gets very large during the broadcast, and then it gets small again back to the background. So that we've got a pretty well-defined broadcast region. But you can also see that the top and the bottom edges of this are, they sort of bounce around a little bit. And that is caused by the frequency wandering that I mentioned earlier. So one way to think about how to approach this lab is to look at this plot and say, okay, I want to write some code that massages the height of this to be much closer to flat. And the way you do that is you set up your computer program to go, okay, I expect the next data point to be here, right? And then you compare your expectation to what you actually got. And using the difference between your expectation and reality, you can adjust how you calculate what the next expected value is. And the looking forward predictive adjustment process and how you recalculate the calculation of the expected next point really tripped up students. There is another way to think about how to approach this problem. So if you take this plot and rotate it sort of 45 degrees out of the screen, you get this plot where you see on the left-hand side, there's the little strip that's the small noise segment. And then you get this broadcast where the transmitter is broadcasting some vector in space. And the size of the cylinder is the total broadcast power. So the previous plot was looking at it from the one angle. This is sort of rotating it. And then if you keep rotating, you're looking end on, and you get this plot. So you don't see any time information in this plot, but you do see both parts of the imaginary data that you're working with. This center part is, again, the low power noise, background noise, and then the outer ring is your Bluetooth packet. And it was not broadcast as a ring, it was broadcast as some number of discrete points. And the other way to think about this correction step is to say, okay, with the frequency wandering, that causes the points plot to spin around. And I'm trying to come up with some predictive correction to stabilize it and keep it from spinning around. This is, in fact, a solved problem because your phones work. And if you couldn't do this correction, wireless comms just wouldn't function. But it is not solved in a way that is easily accessible to students using the format that Bluetooth is broadcast in. So if we go back to here, Bluetooth is broadcast as there's some imaginary center line and you're bouncing one side or the other to tell it if it's a 1 or a 0. Most broadcasts don't actually change the frequency they're on. They just sort of broadcast up the middle and then maybe that wanders a little bit and they change other properties of the broadcast. So if students look up, hey, how do I stabilize this plot? They often get results for systems that just have a centerline broadcast, and those aren't, the solutions you use to solve those are not the same as what you use to solve the problem for Bluetooth. So students generally spend a lot of time fighting their code and not really getting it to work. We have had a few student teams over the years succeed in actually like solving this problem for Bluetooth. But not many of them do. The cheeky secret is you don't need to do that. Because Bluetooth has such a big difference between a 1 and a 0, you can ignore this step and keep going. I don't tell that to students until they've struggled because I want them to know the concept, but they don't actually need to succeed to finish the labs. The next step after this is taking this data and turning it into 1s and 0s, which is essentially looking at this plot and going, is it on the left or is it on the right? And then you find your packet and you write a bunch of code that implements this series of plots, which is the Bluetooth packet spec or the unencrypted advertising packets. So you've got, you know, some beginning broadcast stuff, a payload, some ending broadcast stuff. Then in the first layer of payload, you've got more beginning information and another payload. And then in that, there's more beginning information and then some number of sub payloads. each of which has more information in it. Students usually get to about here and things crash, but they're generally able to convert these advertising packets into some meaningful amount of information. So they can run their code and say, oh, hey, look, I found X, Y, and Z packet from this device. I'm not entirely sure what's completely in it because I ran out of lab time, but I found the packet. I got all the bits. We're good. Is this okay? So that is the overview of the lab series. Now we get into, I ran it for 3 years. What did I do between the years? We had the 2020 edition, which was right before I entered. And then going into 2021, Linsky and I created this new lab series for the fully remote course. 2022 was mixed remote and in-person. So about half of the class was remote, half of the class was in person. So we needed to preserve the ability for remote students to be able to do this set of labs. But based on the results from the first year, we adjusted what the stated goals were. So the first year we said, we want you to be able to take these advertising packets and decode them to the point where you can get plain text device names. So you know how when you're pairing your phone to your headset or whatever, it'll say Gary's headset. Okay, your phone has to know what the name of your headset is, so that's transmitted somehow. And the original goal was, hey, capture those packets, decode them, and get some device names. And we discovered that most devices will only broadcast their name in response to a specific request. So there weren't all that many of these device name packets flying around, and students weren't able to find them. They were able to decode packets, they just couldn't get any device names. So we said, hey, the new goal is just decode some packets. And we also had some issues aligning topics when they showed up in the labs and when they showed up in the associated lecture series. So we rearranged some of the lectures so that students weren't encountering information in the labs before they had some formal lecture about the topic. We ran the labs again. It was mixed, remote, and in person. We had better results. The big pain points of lab 4 remained. And then going from the second to third year, the third year was fully in person. So we had the opportunity to have a custom transmitter. And that allowed us to fix some pacing problems that we were having in the first 2 years. So to go from this point where you've got your semi-stabilized plot to I can decode most of a packet requires almost all of your decoding code to work in one go. And a lot of students were getting to that point and coming to me and saying, I think my code works, but I'm not getting results and I don't know why. And, you know, I knew how everything worked. I could look at their code and say, hey, you need to look at this part here, that part's not working right, or it's not working how you think it does. So they were able to progress by coming to me as some sort of oracle and saying, hey, your issue's here, but they were having a very hard time moving forward on their own. Using a custom transmitter, we could make some intermediate stages where we were broadcasting something that wasn't Bluetooth. And then we were broadcasting something that was kind of half Bluetooth, but skipped a lot of the hard parts. And then we could broadcast a fully compliant Bluetooth packet and say, hey, if you can catch this one, your code's good. And it also allowed us to have our broadcaster could be broadcasting some sort of device name without a previous request. So students were more easily able to say, oh, hey, I am decoding everything correctly because I'm getting the message I expect to be getting. The other thing we changed for the final year was some visualization techniques about, which way do you plot things? Do you plot it from the side view or the donut view? And which one you do changes how students are thinking about things. This is an image of the custom broadcaster. So at the bottom, earlier in time, we've got a really slow packet. So, and you can sort of see that the brightness is jumping between sides. And if you zoom in on that, you can, with a ruler and a pencil on a piece of paper, say, oh, hey, I can decode this just with my eyeballs. Yes.
So, and this is very important because this connects the second important sort of requirement of the PhD experience, which is the proposal, which is done only between PhD student and the committee. What motivated this custom broadcaster? Because we didn't use it in any of the other ones before this point. So this is kind of very, very important because it shows that continuity of the PhD experience.
Yeah, a lot of the motivation for this was both student feedback and discussions with Professor Michelson, who brought up the sort of the pacing of the course and could we fix some of these, really big jumps in required student ability here. So on this, we have a really easy broadcast down at the bottom. Students can decode it by hand with their eyeballs. And then we get progressively harder and harder and closer to a real Bluetooth packet until they are required to use some sort of programming techniques to automatically process the data instead of looking at plots and spending 10 minutes decoding it. Going into the course evaluation data, at the end of every course, students are asked questions in an online form, and some of them reply. There was a set of 5 lab questions related to the lab specifically, which are the questions that I was focused on because I was working on the labs, including proper use of equipment, whether the equipment worked well, quality of lab procedures, how hard it was, and how clear the goal was. So we're covering how easy is it to do the lab if you already know what you're doing, and how easy was it to figure out what I'm supposed to do, and how hard was doing it. And here's the big chart of results. So the left 3, 2018, 2019, and 2020 are from before I entered the course. And 21, 22, and 23 are the 3 years I did. And all of the numbers got bigger. Look at that. And I think the more important part here is that the numbers are a lot more consistent year to year in the second half. So it's not sort of a crapshoot what the students are going to think going in. You've got some sort of a decent idea, and then if students are really struggling, you can take a poke. Just because of time constraints, I'm going to be going a little bit faster. I wrote a bunch of code to hand to students for future generations of learners to reduce the amount of, everyone has to write the same code to even start the radio. Let's just do that all for them because it's different for every radio. They can learn that later. All the students don't really know what they're doing. Their code ends up an organizational mess. Let's provide sort of a boilerplate template to do that for them. And I lastly wrote some example code to say, okay, the labs end at I can decode Bluetooth packets. Let's take that a bit further and, you know, there's multiple channels that these advertising packets can show up on. What if we could do all of them at once? We'll skip the demo. It works. Okay, we can do the demo. We're getting my radio, which is a fancy one.
And it's not $250 and it's from.
Oh no, this is a $1,000 radio from eBay that I purchased used because you can't buy them new anymore. Oh, okay. You guys can't see that.
Unless you put it in front of the camera in front of them.
Now you can. Look, data packets. So we got a few hundred packets from 10 seconds worth of data collection. And most of these are manufacturer specific data. I think that's Apple devices. But sometimes you'll see one that's, you know, some flags, some service data. Occasionally you'll get a name. Sometimes you get something that isn't in my lookup chart. Then we get into, can ChatGPT? Yes.
Were those packets smart devices?
Yes.
Actually?
Yeah. So your people in the room are going to have stuff that this can see. Much beyond that, you won't be able to. So.
Other questions?
What is CRC? I saw that some of them failed.
Yes, so CRC, if we go all the way back to here, CRC is the last portion of the packet.
Okay.
It stands for cyclic redundancy check. And basically, you do a bunch of math, check it against that and say, hey, did I receive what I was supposed to? If any of the bits are flipped, the CRC will fail usually. So that was just to check for, did I get good data or not?
Any other questions? That's why always turn off your phones with Galahad.
Yeah.
Can ChatGPT do the labs? This is a question that came up the third year I offered the course because some students attempted to answer this themselves. No, it almost can, but there's a lot of specifics of the steps that it struggles to do, like calculating the CRC, it screws up. It doesn't really understand the packet format but it pays lip service to knowing what it's doing. So a student that doesn't know what it's doing can't look at its output and say, oh, I know that's wrong. And that's the real issue with using ChatGPT, is that it's wrong and students can't tell. Future work would include improving the project guidance, reordering the labs a bit. So taking the two sort of correcting things labs and moving them outside of the context of Bluetooth would allow students to work with a different transmitter type that you could then Google information about. And fix some scalability problems. So the way the labs are currently structured relies on me being very, very good at knowing what I'm doing. And that's a problem for if someone else was going to TA this and they didn't already have a master's degree in Bluetooth. So there's some ways you can fix this, including using the code framework, because that helps fix organizational problems, which was a big issue. In conclusion, these are the 4 things that I started out saying I wanted to do, and I did them. This is a list of my publicly available work, including 2 presentations at New SDR, which is the New England Software Defined Radio Conference that we hold here every year. My dissertation, Modernizing Undergraduate Software-Defined Radio Education, covering 11 chapters and 315 pages, which is aimed at teaching staff. I'm also publishing the existing lab guides and the code framework. And Dr. Blinsky and I are working on a guidebook aimed at instructors and students, called something like Hands-on Software-Defined Radio Experimentation. It'll be about 100 pages plus associated documentation. And we take the lab series and we spin it to be, or we take the discussions around the lab series in my dissertation and spin it towards students. There's a lot of background information that I wrote about that the teaching staff would need to be aware of, that the students themselves don't need to know. And that's going to be published through the WTI Press sometime next year. I'd like to thank Dr. Waglinski for being an academic advisor for 8 years at this point, and just really supporting me through this. Doctors Michelson and Walls for being helpful committee members through this process, and my friends, many of whom are here.
We love you.
I currently owe the federal government $5,284.52. If you would like to donate to reduce this number, I accept pretty much any way you could pay, because I don't want to owe the government money. This is the coolest plot I've ever done, and I couldn't figure out a way to shoehorn it in. Someone asked me about this.
What is it?
Cool. Oh, no, sorry, we're not at questions yet. Now we're at questions. I heard someone ask me what this is. If your radio is taking measurements of the electric field around the antenna, there's a limited amount of loudness that it can measure. And if you go beyond that, you're essentially blowing eardrums off your radio. That's this bounding box here. If you're within the confines of that bounding box, the unclipped signal in green here, everything's good. If you're right up against the edge of the bounding box, you start to introduce angular errors to your data because everything's moved directly in. So if you had a point like here, halfway up and slightly outside the box, it actually gets rotated towards 45 degrees by the clipping. But you are still able to unambiguously determine relative angle direction. So if we remember, we were trying to figure out if Bluetooth is, you know, to the left or to the right of the center. That has to do with what angle it is on this chart. So if you only clipped a little bit, you can still figure out whether something's on the left or the right. But if you've got an incredibly loud incoming signal and you're off this corner point, you can no longer tell the difference between the angle of your points. So at some level, you can't decode your Bluetooth signal anymore. And what that level is depends on your sampling rate and a couple of other things. But we had a lot of students that set their gain control way too high and just got a box, and yet they were still able to decode the Bluetooth signals. So I was figuring out how that works.
So I'm thinking, if you're okay with it, to stop recording.
We got something in chat.
Yeah, I see that too.
Yeah. One dummy question here. Without the square in it, it looks exactly like the Wi-Fi logo. Is that for a reason? Like on your computer, you click on Wi-Fi, it looks the same. Is there a reason for that, or?
No.
Okay.
Okay, so let me read this out to the audience in case you need, like, so question to Galahad. This is from Professor Clancy. What parts of this work represent original contributions of knowledge to the field? I'm thinking about technical contributions and or teaching contributions. Much of your technical challenges to the lab seem
represent pre-existing technical knowledge to the field true? Yeah, I'm trying to put like the double question mark. Were any of the teaching methods novel to this topic? Are the teaching materials novel, and if so, compared to what? Many or most similar courses use some sort of lab, so how are these labs distinguished? I think I got all of that. So.
Yeah, so the concept of having a lab isn't new. The distinction here is, and where the contribution to the field is in sort of the cohesive approach to, we're analyzing this from the perspective of we want students to be able to learn it, and not we're just taking some research project we're already doing because we're research focused and stuffing it into an undergraduate lab. Many of the other courses I found information on were largely network focused projects. So you'd set up your radio, you'd get them talking, and then you'd do something else instead of spending your time focused on using the radio and most other people.
So
Yeah.
Galahad, if your interest was in student learning, how did you assess student learning?
I'm sorry, can you repeat that? I didn't hear it.
If your interest was in student learning from the labs, how did you assess student learning?
The publicly usable assessment is the
Well, you might want to go.
yeah.
I want to go back to the historical perspective of the last 6 years.
So this is course evaluation data for these lab questions. So we see a fairly substantial improvement in
Maybe go to the
responses.
It's at the previous slide. What numbers 1 through 5?
Yeah.
Right.
So we were looking for pretty high values in all of these. Ideally, you'd get a 5 in all of them, except maybe the intellectual challenge one. And we
So on the lab assessment on slide 27, what was the sample size?
the sample size was 6 to 10 students per year.
Yeah, do you think those changes are statistically significant with 6 to 10 students?
I did not do that assessment directly, but that represents about a 50% response rate from the course. Yes.
Maybe just to throw in there, when doing the background check in places like IEEE transactions on education, that sample size seems to be consistent with practice in other peer-reviewed published literature.
Okay.
Sounds good. All right. Any other questions from the audience? Yeah.
You see like devices that are increasingly popular like Flipper Zero that are kind of similar that are similar or I think might actually be software defined radios. Is that something that you considered using?
The flippers came out after we started. We did actually have pretty extensive discussions about switching to using Flipper Zero specifically. It didn't cover, if I remember correctly, it did not cover the 2.4 band. And we looked at other communications technologies that we could use with the flipper, and there wasn't anything that hit the sweet spot of difficult enough to, be representative of a 4,000 level undergraduate course, but still achievable. Those are used for things like RFID badges, and those are completely encrypted, and there's very little you can do with that as an undergrad student.
That's a good question. Any other questions? Go ahead.
I don't know how important of a question this is, but can you elaborate on how Zoom as a technology? I noticed that if I'm not loud enough, it doesn't pick up on some things, but if I'm at a certain volume, it does. So when I play D&D and I make little squirrel sounds, they don't come through, but my voice does.
That actually has to do with this plot, sort of.
Okay.
Zoom and these radios use something called automatic gain control. where they try and put this unclipped signal as close to the edge as possible. Because you get better data that way. But they also have the ability to block out background noise. So if you're not talking loud enough above your background noise, it thinks it's just like a car driving by, and it's not going to recognize that as a different signal, if you will, from the background. So it's not going to actually turn on the microphone and send that to someone else.
So that's really close to the threshold.
Yeah, and then if if you're really quiet and you scream into your microphone, it sounds all wonky. That's you exceeding this bounding box.
Third questions? Anyone online, any additional questions? All right, so let's thank Galahad for a great presentation. So now we're going to enter the lightning round. Double Jeopardy.
You can stop recording.
Oh, I think I did.
It says it's still recording over here.
From Alex to everyone. Okay, thank you, Alex.